Thank you. Yeah, we're recording now. Yeah, welcome to our demo day. We hope you finished finals strongly and the very chaotic semester strongly. As many of you probably know, PI is Claremont's AI project incubator and community. We host AI projects for 5C students. You can check us out at www.p-ai.org, or you can email us. And today we're going to be demoing some of the projects we did during the semester, as well as talk about our plans for next semester, including some of our industry internships we'll be offering. You can change the slide, Andy. Yeah, so some of our milestones which we've accomplished in the past semester and year, we've recruited and onboarded a record-breaking 100+ students at the 5Cs, and we've sort of trained them on the basics of AI and ML through projects, workshops, and we've also hosted a variety of events in securing internships. We've had alumni come in and talk about their experiences, and as I mentioned earlier, workshops. And we've also closed partnerships and projects with Samba TV, TradeWeb, and NAPFIS, who you'll hear about later in the event. And our members have gone on to do some pretty awesome things in AI, from engineering to ethics and policy research to startups to the usual suspects, FANG, Amazon, Facebook, Google, et cetera, et cetera.
Cool. Hey everyone, my name is Andy. I'm the current director of projects at PI, and I'm really excited to share the 6 projects that we've been working on this semester. So we have a really wide range of projects that we put a lot of effort in, and we hope that learning more about them will be an enjoyable experience for everyone. So this semester we've got P-Deepfake, featured extraction of deepfake images, led by Danica. We have P-Interact, applying GPT-3 to interactive fiction. TCM, which is bridging traditional Chinese medicine with modern nutritional science. Climate, which is reconstructing climate signals from natural records. Spike, decoding neuronal signaling for seizure detection in epilepsy. And Resume, which is NLP-enhanced resume generation. So I'm going to pass off to Danica, who's running P-Deepfake, to talk us through her team's progress this semester.
Awesome. Okay, so hi everyone, my name is Danica, and our team today will be talking through the project P-Deepfake from this past semester, where we explored and analyzed feature extraction algorithms in the context of deepfake images. And the project members for this project are Marwan, Ishan, Vani, Austin, and myself as the PM. So now I'll hand it off to Marwan to get us started.
Yeah, thank you. You can move to the next slide, please. So first, we just like to talk about what deepfake is in general. And deepfake is just an umbrella term to describe the creation of synthetic media using deep learning or machine learning techniques. Next slide, please. So here we just have a few examples of deepfake media. So on the left, we have this example of this random person who had, and then the deepfake version of this image, which is an overlaid version of Tom Hanks. And so you can see how we use real media to generate synthetic media using deep learning techniques. Well, next slide, please. And one thing that's very interesting, which sort of motivates the project, is sort of the ethical concerns that come out of this. So the thing that sort of comes out of this is that we have very easy to make convincing synthetic media, as shown through this information piece, where Jordan Peele shows how dangerous deepfake media can be in spreading misinformation. Next slide, please. So in our sort of analysis of deepfake images, we in order to get data, we used feature extraction algorithms, and 2 of the big ones are SIFT and ORB. Now, what these extraction algorithms do is they take an image and they return key points, which are just a set of points on the image. And then from these key points, we have feature descriptors, which are generated, which are like the footprint of the image. And our general sort of idea here is we wanted to look at real fake image pairs and then see what happens to the key points in the feature descriptors when we look at what happens to an image when it's a deepfake is created from it. So in sort of like these classical image detection algorithms, it's really well understand what happens to images when we like stretch them, rotate them, shift. But we want to know what happens when we create a deepfake on that image and how the data changes.
All right, so just to talk through our basic approach a little bit, it was pretty basic. We basically had 3 phases: a research phase, and then an exploration phase, and then an analysis phase. So about 2 to 3 weeks each. Research phase, pretty simple, data set creation, and then another team doing algorithm exploration, just getting familiar with the Python side of the implementation, and also just choosing which algorithm is best for our use case. So we mainly studied SIF, SIRF, and ORB. And then obviously the data set came from the Kaggle Deepfake Detection Challenge, which was a huge challenge that was ran a couple years ago. And then once we moved on to the analysis part, we had about 1,300 folders with 100 video frames each. It was around 20 gigabytes total, so a pretty hefty data set, but not massive when it comes to ML. And then our analysis was split into 2 parts, which was analyzing the average number of feature points in real versus fake data, and then also the average number of feature point matches between successive frames, again, in real versus fake data.
All right, and right here is just we're going to talk about data creation a little bit. So the data set that we use to generate our data is this Kaggle benchmark deepfake data set. And that just it's a benchmark data set because it's been used in a lot of deepfake research. And the way that the data set is organized is there's a bunch of videos, and then each real video has a corresponding deepfake video. And we use those images to generate those videos to generate images. And over here, we can just see what we did is for each one of these videos, we then generated another folder, and those each one of those folders contains images of the frames. And then each one of these frames, we just crop the face. And the reason why we crop the face is that we're trying to reduce noise, and so that we only get data regarding the face, because this is where we're trying to see do our analysis. And being able to just crop the face means that we don't have any noise when we crop for facial regions. And the reason why we crop for facial regions is it allows us another layer of complexity, so we can see how the data changes during this cropping. And over here is just a general overview of how the data generation was created. So we, in the data set, we went through all real fake image folder pairs. And then for each matching frame image, we extracted the facial regions and then ran the SIFT or ORB algorithm to get the key points and the descriptors. And then we dumped that information into the corresponding CSV file for that facial region. So we're left with just a bunch of CSV files which contain a lot of real key point and fake key point pair data for that facial region.
So for our first piece of analysis, we wanted to compare the average number of feature key points for deepfake versus real images, and see if there was a relationship between the number of features between them as well for each of the regions. So for ORB, we found that generally for the data set that the distribution of key points was right skewed, and that the average number of key points per image for the real images was greater than the average number of key points for the fake images. We also, when comparing the number of key points for the real versus fake images, we found there to be a positive correlation for only the jaw region. We didn't find there to be any kind of correlation for any of the other regions. Similarly, we did an analysis for the SIFT algorithm as well, and we found that the distribution was right skewed for almost all the regions, and that the average number of key points for each region was greater for the real image data set, again, for almost all the regions. And again, only the jaw region seemed to have any sort of positive correlation with the number of key points. And this is just another graphic showing that the average number of key points for the real images was greater for most of the regions, in this case for the SIFT algorithm. And I guess the key difference between the SIFT and ORB algorithms were that SIFT generated a lot more data, so that perhaps would be more useful when using it to compare the images in the future, because it gives you access to more data about the image.
All right, and then for our second point of analysis, as we mentioned earlier, basically what we did is we compared frame 1 and frame 2 of a fake set of data, and then frame 1, frame 2 of a real set of data. We wanted to see, okay, so if we do keep on matching between these frames, is there any difference between the real data set and the fake data set? So what we used here was something called the Lowe's ratio test, which basically says, okay, we're going to take one key point, and then we're going to compare it to the 2 best matches on the target image. And then if the best match is not sufficiently different enough from the second match, we're going to say, okay, it's probably just a noisy match, and toss it out. So this results in some pretty good matches. You can see that on the left, which is an example from the documentation. Even when the object in question is rotated, we still get pretty good key point matching, and there's not that much outside noise. And then on the right here is an example from our data set. I believe this is a deepfake successive frame. And as you can see, the person's matched pretty well, but everything else is not, which is exactly what we wanted. Next slide, please. So just to generate a data set, it was pretty simple. CSV files with data we wanted, and the data that we're analyzing in this case is not only the number of matches, but also the average distance of matches, which we defined as how good the match is, because basically if a match is further away from one on the target image, it's going to be a worse match. So that's pretty simple as well. Next slide.
So on the top, we have the fake match and real match data of each successive frame using SIFT. And on the bottom, we have a similar plot using average fake and real distances. So there's not a lot of interesting analysis here, since the matches were roughly the same for each pair, which kind of makes sense since it's a comparison between successive frames. However, if we look at the next slide, which has similar results, what was produced using the orb algorithm, it is interesting to note that the difference in key points between SIFT and orb, because we can see that orb produces less key points on average than SIFT, which matches the previous analysis. So to sum it up real quick, we did not find any meaningful correlation between real and fake images using successive frames, but it was still an interesting avenue to go down. Okay, so we accomplished some pretty cool stuff this semester, as you guys saw in the past slides. However, if we had more time, there are a few more things we would like to do. So this includes performing a more complete and comprehensive analysis of the data, where we explore different metrics, including analyzing real and fake images using different pipelines, including scaling and rotation, and comparing those key points to deepfakes to see if we can find any sort of pattern. We did do a preliminary comparison this semester, but it would be interesting to compare the efficacy of each model like SIFT and orb in more depth and explore other saliency-based algorithms. We could also feed our findings into a classification algorithm like a CNN, using the trends we discovered for some more predictive type modeling. So while we did a lot of interesting stuff this semester, there's still a world of cool things to explore in the deepfake space. Any questions?
Great, thanks very much, Deepfake. Who's next, Andy?
That would be me, yeah. So hey everyone, thanks for that great presentation, Deepfake. So we are P-Interact using GPT-3 to generate interactive fiction. The team members are Zach, who unfortunately is ill and can't make it tonight, Imuna, David, and myself, Andy. So just a little bit of context on what this project entails. So a few years ago, OpenAI released GPT-3, which is some cutting-edge transformer-based language model, and it's been really effective at creating basically human-sounding text, owing to like a very complex structure and a lot of advances in transformer technology. So you can see that it's actually pretty good at creative writing when we give it these shorter prompts. So here it's writing a 2-sentence horror story, and it can also do a lot with short stories. So a lot of people have worked on trying to adapt this into the realm of interactive fiction. So the biggest example here is AI Dungeon, which is a text adventure based around GPT-2 as an engine. So it's been found that AI Dungeon does a really great job in the short term of generating like human-sounding text and these realistic setting depictions. But in the long term, it can often struggle with coherency and consistency. So our goals were kind of to start with this toy problem of a choose your own adventure. So this is sort of story where the reader occasionally gets like different options, and depending on what option they pick, so like for example, the top right, they can be however the story proceeds is sort of up to them. So we sort of view this as a good way to bridge the gap between short-term realism and longer form coherency, because this is sort of an easier task than responding to literally any action like a text adventure, but it also provides more opportunities to look at long-term coherency.
Yes, as Andy talked about a little, when we first looked at the 2-sentence horror stories from OpenAI, the goals we developed for our project were, one, for the AI to have like the ability to give 4 choices for the user to choose from, and second, for it to be able to like keep track of all the past text and all the past user input when coming up with new choices. And then third, after the user chooses from one of the 4 options, it will be able to create another prompt and another 4 choices as like a continuous pattern for as long as the user wants. And then we also worked on making sure that each option was unique and didn't have any repeats. And then we also worked on like tuning it to making sure it would flow and also make like actually tell an actual story.
So how we actually encoded and summarized our stories. The challenges that we had for this, because we're working with continually generating text, we have to find some way to encode our previously generated stories and keep the storyline consistent for human readers. We also have to keep track of previous and current story states, how far along we on the plot. And we also have to figure out how to continuously incorporate user input into the generation loop for our storyline, since we do aim for this to be a choose your own adventure format. Next slide. So we actually use another aspect of GPT-3, which is the ability to create TLDRs, or too long didn't reads, like few sentence summaries based on input text. So on the left, you can see a big paragraph which you don't have to read, but the important part is that the bottom gives you a TLDR where you can get the gist of the previous text. On the right, we also consider using a tabular format to encode our data or previous story states, but it was inconsistent, and using TLDRs basically was better for a better breadth of story. Next slide. So how our story generation loop worked was our model will give you an initial prompt, then based on a user choice that the user had selected, that's prepended onto the next story generation. Then that entire story generation with their user input is then turned into a TLDR, which is prepended onto the next story generation, which becomes our final story generation loop. As long as the user keeps selecting choices that keep the story moving in a coherent way, then in a true choose your own adventure format, the story will also keep moving. Next slide. Okay. So the TLDR of this is that we essentially change GPT-3 settings to use TLDR to summarize our generated story as we continuously as we generate our story. It's more consistent and can be applied to broader categories than quantitative style approaches. And it allows for clean user input insertion, as we can just prepend it onto the user choice. And at the bottom is just GPT-3's TLDR of that. Next slide. So then for optimizing and evaluating our hyperparameters, 3 hyperparameters that we determined to be the most important were temperature, which controls randomness and how deterministic the text is, frequency penalty, which controls how often an idea is repeated, and presence penalty, which is the penalty for introducing new ideas based on if an idea already exists in the text. So we first focused on a temperature grid search, which was the most important hyperparameter. We evaluated based on different cosine distances, which is a metric used to determine how similar documents are, regardless of how long the documents are. And the framework we used for this was sentence transformers, which has pre-trained models for encoding documents. We used different proximities, 1, 2, and 3 sentence aways, and then we compared their cosine distances, and then we also compared all sentence cosine similarity, which is basically taking one sentence and comparing it with all other sentences in the document and doing that for every single sentence. This was then run, my bad. This was then run across like the entire range of temperatures across intervals of 0.1 or minimum to maximum. And our target value that we used was 0.2, which is based on the short story, or based on the cosine distance for the short story, The Egg by Adam Ware. So this is our data, or here are the results that we got from our temperature grid search. You can tell that the 1, 2, and 3 distance away cosine distances were pretty similar. The all cosine distance is a little bit more interesting and more closely approaches our target value, especially when the temperature is set to be around 0.3 and 0.7. So these would be the optimal temperature settings that we want for this hyperparameter. Otherwise, it follows similar trends with the rest of the proximity distances. Next slide. So further ways to optimize and evaluate would be to tackle more hyperparameters with a more complicated grid search. This is a perfect opportunity to use a neural network to train over more samples of generated text and more cosine distances. And then we can use scikit, which is another Python library, in order to tune hyperparameters of grid search. We can also use metrics other than cosine distance, one of which is deep coherence, a library for holistic text coherence analysis, or soft cosine measure, which is a little bit more lenient and arguably a little bit more organic than strict cosine similarity.
Cool. So now we have a quick demo for you guys about our what we ended up making for pinteract. So I'm just going to play the video now. Hey everyone, so this is the pinteract demo for demo day 2021. And so what we have here is a Streamlit, so that's sort of a design framework for data scientists. It's a quick framework to serve as sort of the container for the engine behind making all the GPT-3 API completion calls. So what we have here is a sci-fi-esque story prompt. End of the 21st century, the place is Earth, and we have a party for the Secretary General of the UN, which apparently collapses within 10 years, which is not great. And so it gives us a few different options for completing this, you know, what happens next. And so this prompt is actually also generated by an OpenAPI call. So basically we told GPT-3 to sort of start a story written that we told it was written by Isaac Asimov. And so this is its best approximation of what that looks like. So you can kind of see it like the vaguely sci-fi impact. Cool, so we are going to pick two here. The party is being given by the old friend, the former president of the US. He was a general in the US when that also collapses in 10 years. And so now we have a little bit more on there. You know, we have some stuff on. And it's going to take a while to load. So what this is doing here is it's sort of generating the continuation from this prompt one. And then when it's doing that, it's updating the summary, and then it's generating a new set of choices for the user to choose between. And so basically, it's just going to keep doing this iteratively until the user is finished. Cool. So yeah, that was.
Okay, for next steps, our proposed next steps are: 1, more prompt generation and genres for users to choose from. 2, we currently have 4 choices generated after every text, and the user chooses for one of the options and the AI continues from there. But it would be great if like in the future, after choosing one option, if like the users could like go back and trace where the other 3 options lead to like different storylines. And then 3, it would be great to have more web development on Streamlit in order to have like a better UI experience for users compared to websites like AI Dungeon. And then 4, finally, it would be great if like we could implement more prompt design in order to incorporate more diverse authors and diverse writing styles. Thank you for listening, and also a shout out to Zach that couldn't be here today with us.
Yeah, thanks for that. So like I said, thanks to Maimuna and David, and like they both said, there's a lot of really cool directions this project can be taken. So we are planning on recruiting for additional project members next semester to just lighten that load on each individual. So if you're interested in this kind of thing, just let me know offline. And yeah, if there are any questions now about our work, just now is the time to ask.
I have a question. Is there a particular reason why you used the egg for temperature for like a temperature optimization, or?
Oh, well, so we wanted to compare it to a like short story that already exists. So we have like a metric or basically like a target metric, right? And someone had recommended to me the short story The Egg earlier this semester, and I really enjoyed it. So I thought, I don't know, it's a good story. You should read it if you get a chance.
Along the same lines, when you're calculating cosine similarity, were we doing that on like all the cumulative word vectors of the entire story?
Yeah, so actually, because it's like continuously generated, we went for across like these different ranges. So every interval has basically we generate these text files, which are a few responses in or a few story generations in, and then it would be along the vectors of every sentence.
Gotcha. And were those were those like embeddings that you had trained, or like word to vec? Which how did you get those word vectors?
Oh, those word vectors, what do we call it? Sentence transformers has pre-trained models. So we just use some of those pre-trained models.
Oh, yeah, Jacob, go ahead.
Yeah, that was really cool. And I was wondering if you had any ideas on potentially having the continuous generation aim for a particular conclusion or aim to introduce a particular concept down the line. Have you thought about any sort of planning that can be involved so that you can maybe shape the structure of the overall narrative a little bit more?
We talked a lot about like having like characters and keeping track. Like we wanted to do, like, it was around like Halloween, we wanted to like do like a horror film and like keeping track of like the people who died and people who were alive and seeing if like the AI would be able to keep track of stuff like that. So like we're like looking into things like that also in the future.
Yeah, that's definitely something that we want to look into more as we move into next semester. I was just introducing more control into the prompts. But yeah, I think that was about the extent of that we actually looked at it this semester. Cool. Yeah, thanks for the questions. If there's nothing else, I'm going to pass it off to Aaron to talk about PTCM.
Am I sharing the right? Let me. Can everybody see that? Cool. So hi, we're at PTCM and we'll be sharing about what we've found and learned in our project this semester on connecting traditional Chinese medicine and modern nutritional science. So to start with some background, in traditional Chinese medicine, each food is categorized into hot, cold, neutral, and more categories in between like cool and warm. On the other hand, modern nutritional science looks at food through its micro and macro nutritional properties, vitamins, and so on. We're interested in if modern nutritional science can predict the TCM groupings, and if so, which food property were the most important in prediction. We started at the current stage of research and found that among the multiple papers published on the subject, there's not a clear consensus. We spoke to one of the authors of a recent paper and designed this project to extend that paper. We used the same data set as they did and relied on their literature review to get a TCM property of each food. However, in the methodology, we used machine learning algorithms rather than statistical methods. I'll now pass on to Shreya to give a quick overview of the data we worked with.
Yeah, so for an overview of our data set had 241 different foods with 34 nutritional values for each. As mentioned before, we got our initial data from Professor Kong, whose lab had already done a literature review and classified foods as different overarching temperature categories, which are hot, plain, and cold. Taking into account food overlap in different categories, we ended up with 8 final temperature categories, which were heavy cold, cold, cool, plain, warm, heavy warm, hot, and heavy hot. And a second approach we took involved using just the original 3 categories, so hot, plain, and cold. And as shown in the pie chart, about a third of the foods fell into each overarching category. Next slide, please.
Hi, I'm Eric. So I'll be talking a little bit about how we handle our data. So at first glance, our data that we got from Professor Kong actually had many null values that needed to be cleaned. So essentially, as you look to the right, this is how many null values we had for each of for a few of the top inputs. For example, like iodine had 167 missing values, which is a little bit tragic. And then if we normally in data cleaning, we would just delete all the columns without each of these values, but that would result in us not having many data values to work with. So we use another solution. So we use an iterative imputer instead. So basically, all we do is we just take these feature sets and then we basically impute them, and then we look at other columns and values, and then we fit each data point to these values. And this allowed us to maintain our size of our data set while still having accurate amounts of data.
Yeah, and so we also wrote a function to calculate what percentage of each food fell under one of the 8 temperature categories, and another to calculate a value for each food on a linear scale, ranging from heavy cold to heavy hot. We also wrote a label encoder function, which converted categorical values into numerical values. So in this case, the food names into numbers. Next slide, please. We also wrote a function to normalize the data and to make the different nutritional values comparable by standardizing each value by scaling all values in a fixed range from 0 to 1. Our initial approach involved trying to account for every overlap between temperature categories, hence the 8 different temperature categories. However, we found that this method led to lower accuracy overall for the machine learning algorithms we tried. Our second approach involved using just the 3 original categories of hot, clean, and cold, and we found when doing that the accuracy more than doubled. Next slide, please.
So one of the machine learning algorithms that we applied was the logistic regression model to our data set. And the logistic regression model essentially is a classification algorithm that utilizes the sigmoid function to map predictions to probabilities that something is a category. In our case, we used a multinomial classification where the values 0 corresponded with the property plane, 1 with cold, and 2 with hot. You can see to the side a binomial logistic regression model here, which would use the value 0 to 1 and is also nonlinear due to the weighting of each of the dependent variables. So after applying the logistic regression model to our data set, you can see to the side here that it did an overall all right job at predicting each of the food's overall category of plain, cold, or hot. Next slide, please.
So another algorithm we used was SVMs, or support vector machines. So basically they're an algorithm built for classification. So normally they're used for a linear classification, like if you had a lot of shoes and you had to classify them as red or blue, you use SVM. But also there's also multinomial or polynomial classification, which we use to classify into more than one category, one or two categories. So here on the right, you see we have a visualization of this. This isn't for our model, but it's just the central idea that we were able to take 3 different types of things and we split it into like hot, cold, and plain. And then for our results, I need first preface with a description of accuracy, which is versus F1, which is how we measure how accurate our model is. So accuracy was essentially just a measure of how many correct cases we had. Like, for example, we predicted 10 of them right out of 200, which would be a 5% accuracy. Luckily, ours is higher than 5%. And then F1 is a different version of accuracy, which is weighted differently. Basically, we punished false positives and false negatives more than accuracy, which would result in a data that actually cared more about the correct cases we had. So for here, our accuracy ended up being 55%, and our F1 ended up being 50%. So this data is all right. It's not as good as we would hope for, and we'll explain why it's so low in our results slide. Yeah, next slide, please. Another data algorithm technique we used was random forest. So random forest is essentially just a bunch of decision trees that are built randomly, aka the random forest. And then basically, as you can see in the bottom right, each decision trees will make a prediction on each data point, and then we'll take the majority vote of these predictions, which will, so like let's say for 10 of these decision trees, they voted hot, 5 voted cold, then we take the hot decision. And then this prediction by a committee will be a lot more accurate than individual trees. And then something cool about random forest is we're actually look at these individual features and see how important they are in our model. For example, if you look at the top right, so these are all of our different feature sets and how important they were in our model. So our highest is actually protein, which was and then the next highest I think is thiamine. This also did not correlate with the paper, and we will also explain why, explore why this is true. And yeah, in the bottom left, you can see our matrix, which is our result matrix. So 0 is plain, 1 is cold, 2 is hot. So out of the 26 plain, we actually only got 13 of them right, which is around 50% accuracy like our previous model. But yeah, next slide.
So another machine learning algorithm we used was k-nearest neighbor, which is a classification algorithm that uses Euclidean distance to find the nearest k training set vectors or neighbors for each row in the test set, and then the majority vote decides what the classification would be for each object. To the right, you can see kind of an example of what that would look like. And so we found the accuracy for this to be around 49%, which is also, you know, not the best. Next slide, please.
Yeah, so unfortunately and perhaps interestingly, there was not a clear answer. We did not find that any nutritional data to be able to predict hot cold property, and that there was weak overall accuracy across the models. The individual nutrients we found that were most heavily weighted also did not match the ones found in the original statistical paper. This result was perhaps expected. The traditional medicine has yet to be fully explained by modern science. And when it comes to the hot cold property of TCM, the explanatory and predictive power of nutritional science seems to be limited. And this also matches with the lack of consensus in past papers on the subject. However, we still have some ideas for future work, and I'll pass it on to Emily for that.
So some ideas that we have for future work is in twofold. Firstly, training on more data specifically to improve accuracy, and also more focused data exploration on the nutritional properties themselves and their correlations to predicting the overall category of food. And secondly, something else that we could also look forward to doing is improving accuracy for subcategories through defining a more clear scale that would fit each individual model that we could work on in the future. We're also looking towards working on subclassifications of each of the food properties that was also originally researched in the original literature, such as heavy hot, heavy warm, and heavy cold. Thank you.
Yeah, does anybody have any questions for us?
Oh, I just have a question about the kind of like the subcategorization. Do you guys have any ideas on how to like solve the problem of like accuracy like decreasing like significantly when you introduced subcategories?
Yeah, I can take this one. Yeah, so I think like it's intuitive that the accuracy would decrease when you have more of the like more categories to carry. So I think like it will be unexpected if we found that breakdown to like combining like warm and hot into one category, like having just 2 categories wouldn't improve the accuracy. I think that would be odd. So and I guess to answer to your question, like I guess we don't have an idea, right? And that perhaps is something we can explore a little bit more in the future. Yeah.
Cool. Yeah, thank you, Aaron. I think next up we have Sophia and Varun with PSpike.
Awesome. Whoops, there we go. Perfect. Sophia, you there?
Yeah.
Awesome. So we're PSpike. I'm Varun. Sophia's the PM for the project. And then we also have 3 members who couldn't be here today: Lucky, Shinyi, and Serena.
So before we go into actually what our project consists of, we thought it was important to establish a theoretical background on epilepsy and the technology that's measuring the brain signals. So epilepsy is a neurological disorder characterized by excessive or synchronous activity in the brain. And typically this is measured through EEG. So EEG data is broken up into different spectral components and a provided range of frequency bands. And this data falls into 4 frequency bands, which we observed throughout our study and saw how these frequency bands can reflect epilepsy and epilepsy characteristic behavior. So the data we've worked on was primarily from the Siena Scalp database, which is out of University of Siena, and it consists of 9 males and 5 females ranging in age from 20 to 58. While there's not a lot of individuals, they measured progressively these people over time, both when they were controlled by medicine, meaning that they had something that suppressed their seizures, and when they were no longer on medicine, meaning that seizures occurred. The data was collected via continuous video EEG sampled at 512 hertz, which is really technical, but it became really important as we were pre-processing our data. And these electrodes were placed in a standard scaling system, so they're placed on standard regions of the brain. And these individuals have all been diagnosed with epilepsy prior. And throughout the study, they were progressively taken off their medication where the severity of the seizures increased as well as the frequency of seizures increased. And so these measurements were also recorded in time-scaled arrays, which can then be graphed. As you can see here, there's like a diagram of what the EEG might look like, someone occurring a seizure. Here's the array in which the data is stored, and this is how the data could be viewed graphically. So before really doing any sort of manipulation or data visualization, it was necessary pre-processing had to be done. This included filtering out noise to attenuate part of the signal. Essentially, we wanted to remove power line noise, which is a huge impact in all of our data. And I'll show you on the next slide what power line noise looks like. And then we also wanted to resample at different frequencies. This was to reduce computational complexity. But we also made sure we wanted to preserve dimensionality of the data set while doing so. So as you can see, the spikes in this image, those are the power line noise that we were hoping to get rid of. And again, it was extrapolating what that data would likely be without that sudden spike.
Yeah, and another component of sort of removing noise from the EEG data was to implement an autorejector, which is basically taking bad channels and removing them from the data set because they're noisy and we don't want them when we do our analysis on seizure detection. So one pre-processing component which this process involved was to essentially take the names of the channels and make sure they were normalized to fit sort of what was called the standard 1020 montage, which is sort of the industry and academia standard for names of brain channels. So in our code, we sort of had to do pre-processing where we took the names and made sure that the names in our Sienna scalp data set matched up with the names of the channels in the standard 1020 montage. And you can see sort of an example of a bad channel here, where you sort of look at the top two lines where they're way above the rest of the curves. And we used a package called prep to do this and made it super simple. And basically what we then did was we interpolated the bad channels, because when we remove a bad channel, that we have to replace it with something to sort of represent the entire brain structure. So as is shown in the photographs here, we sort of take the information from the closest and neighboring channels, and we sort of interpolate those bad channels with the information of the neighbors. Sort of like how, if you're familiar with like a convolutional neural network, a convolutional layer sort of takes information from the nearest neighbors and applies it to a certain section to get sort of an average for that section. So this is what's happening when we interpolate those bad channels.
So now after that pre-processing was done, in order to build the ML pipeline, we had to do some feature extraction. So this consisted of even more processing steps. These are highly technical. I'll only go into them briefly. So first, the frequency component of the EEG were extracted using discrete wavelength transformations. Then the features, meaning the seizure events, had to be hand annotated. The data set we did, they only had it marked in a separate file when the seizure occurred. So we had to add an annotation of being like seizure event. And then this enabled us to use an epoch structure to split the data into equal size chunks, making an equal size space event array, which could then be used in our machine learning pipeline. And then finally, we rather rushed created a simple artificial neural network with two hidden layers, a ReLU activation function and a sigmoid activation function, which reached an 89.37% accuracy on detecting seizure events. Again, despite this looking really good, it is highly arbitrary because we did do only one experimental study where people were in a very narrow age range. If this were to look at different sort of EEG procedures within different measuring and different facilities, this would likely decrease significantly. So it's an artificially high accuracy score.
Yeah, and so for our next steps to sort of extend this, we obviously want to train it on more data, because as Sophia just talked about, we looked at a very narrow range of data, which is why we got good results. So we want to make the model more sort of generalizable to varying age ranges, varying types of data, and improve the accuracy on those data sets. So those are sort of the next steps for the project. Thank you for listening, and we'll take any questions. Okay, Andy, we can go to P Climate.
Yeah, sounds good. Thanks for that, Bruno and Sophia. Great work. So yeah, our next team is P Climate, led by Hannah Mandel from Pomona. Unfortunately, she cannot make it tonight, but we do have a prepared presentation. So let me pull that up.
My name is Hannah and I am P Climate's project manager. I had the pleasure of working alongside David, Nate, Rachel, Gabriel, Sahil, Karina, and Gabriel over the past semester on a project that lived at the intersection of environmental studies and computer science.
So in this project, we're looking at applying artificial intelligence to the problem of climate reconstruction using natural proxies. So let's break down what that sentence actually means. First of all, climate reconstruction is the process of figuring out what the climate was like a long time ago where we don't really have accurate direct records. So for instance, in the year 1880, there was no one around collecting systematic and accurate temperature data like there is today. So we have to get this information from somewhere else. And what we're actually looking to predict is the anomaly, meaning the difference from the mean over time. The way we do this is using natural proxies. So for instance, here we're using tree trunk rings and data from corals. And we'll talk more later about how that's actually going to get us the climate data. And then for the AI component of this, we're using some neural networks, in particular, the fully connected neural network and the recurrent neural network. The fully connected neural network is just a simple neural network with connections between each of its neurons. The recurrent neural network is a neural network that kind of remembers previous data, so it can predict future results given previous data.
It also really helps to understand what a proxy really is. Starting from the beginning of the proxy process, there's the environment, aka climate events and patterns that exist. To us, the modern scientists, the past environment is unknown. Luckily, we have natural sensors of the environment. Corals and trees both pick up variation in climate and temperature in their physical structures. Corals and trees store this information as an archive in their skeletal makeup. Each ring serves as an annual representation of the general climate activities. We look for specific signals in each annual ring. For corals, we look at D18O, also known as delta oxygen 18. It tells us about a particular oxygen isotope that is closely linked to evaporation of water molecules. It indirectly tells us about the heat of that period. In trees, we look at the physical width of the rings across years. A greater width equates to greater precipitation, which can be related to different temperature climate patterns. To tie it all together, by looking at these proxy signals, we are able to draw a picture of the past historical climate, completing our original goal.
And a lot of prior research has been done with all sorts of climate proxies, so including the two we're using, coral and tree ring data. But it turns out the majority of these models are just using simple linear regressions. And these can perform decently, but it's a problem because the models are just too simple at times and they fail to account for just the noise in the data. And this noise comes from both the general complexity of just the climate system as a whole, and also just from the data itself, since proxies will never be perfectly aligned to what we're predicting with them. And with this in mind, our solution was to use neural networks and machine learning to improve upon the simple models and better capture and predict the complexities behind climate reconstruction.
After setting this goal, to complete these networks, we needed both proxy and temperature data. As inputs to our model, we wanted not only the signal of D18O or tree width, but also the year, latitude, longitude, elevation, and species of the organism that provided the signal. Each of these parameters should impact how the signal is recorded by the specific coral or tree, thus helping us theoretically capture some of the noise in the biological system.
So starting with the data used in coral, we got our data from NOAA, the National Oceanic and Atmospheric Administration. And so within NOAA, we collected all the coral and D18O data starting from 1880. And by collecting this within regions, initially it was separated by oceans. We essentially just combined it into one larger data set, in which we were able to add the temperature data set after our data cleaning process. Our tree data process was actually very similar to the coral data. We also used NOAA and MLOST, but instead of D18O, which is more specifically for coral, we focused on the tree species and the rings of the trees. Like in coral, the specific region of our organisms would affect the results. So we noted the latitude, longitude, and elevation as well. And after cleaning, we added the corresponding temperature data as well from MLOST. So yeah, just really briefly, you can see this visual representation of basically where we got our data from. And so looking at the coral, we can see that it's fairly spread out, but as you notice, it's fairly banded along the equator. So that could be just biased towards tropical regions, which would affect our model. And for the tree data set, you can see that there's definitely a very large percentage of the tree data being in North America and Europe. And so our model would also be biased towards those things.
The data comes to us in the form of many different text files, where each file was an individual study submitted by a scientist or a research organization to NOAA. NOAA requires a uniform file format, so we had a structure to work off of. Once we identified that structure, we were able to use text scraping tools to extract the metadata, such as species, elevation, lat, and long, as seen on the right. And we extracted the actual data table, seen on the right again, which contained information about ring widths for trees and D18O for corals on usually an annual scale.
After we were able to acquire and clean the proxy data, we then added the corresponding temperature data. When acquiring the data, we looked at the year, latitude, longitude, and temperature anomaly values. The NOAA MLOST 5x5 Global Temperature Gridded Dataset is a global surface temperature repository that starts from the year 1880 and goes on to today. Its parameters are determined by the inputted latitude and longitudinal values. The National Centers for Environmental Information, known as NCEI, combines the global sea surface water temperature with the global land surface air temperature into a merged dataset. We then use the MLOST dataset for both coral and tree ring data. When it came to merging the proxy and temperature data, we approached it by taking the latitude and longitude values and creating the 5x5 gridded temperature that laid closest to those given latitude and longitude values. Therefore, we had to then average temperatures across the points that made up our grid to obtain our temperature. Then we had reached the end of data acquiring, cleaning, and prepping because we had attained the temperature data that we were looking for, and we were able to begin model building.
We compared 3 models in this project: a simple linear equation, a fully connected neural network, and a recurrent neural network. First up is the simple linear equation that compares D18O to the temperature anomaly in y = mx + b format. This is the most popular relationship that scientists use. Usually it's D18O divided by 0.22 in that second blue line, but we finessed the formula to fit our scale data a bit. The linear equation is by no means a weak model, but it does indeed have some shortcomings. It does not use any inputs of lat, long, or species, meaning that it's full of noise. And that is very apparent by the high noisiness in the predicted orange signal as compared to the less noisy real temperature signal. It also appears to predict the past as much warmer than it really was, which is an issue for accurate climate reconstructions. We next added complexity to the model in our fully connected neural network. This takes into account latitude, longitude, year, species, and elevation. The top graph shows how the model performed when tested on the same year range it was trained on. It captures the average value really well, but it fails to capture any of the variation from year to year, as displayed by the lower graph that compares the variance of the 2 lines. When we use this same model to predict on historical data, the same trend was visible. It indeed picks up on the average temperature over that period, but does not show any of the variation. Finally, we looked at a recurrent neural network that uses only temperature. Since RNNs are really commonly used for time series problems in machine learning, we figured it would be helpful to try out. It was trained from 2012 to 1960 and then asked to predict 1959 to 1880 temperature anomalies. It predicts each past year's temperature by looking at the previous 4 years' temperature. For example, it uses 1903, 1902, 1901, and 1900 to predict 1889. Overall, you can see that the model performs really well, particularly relating to correlation and variance. It does, however, still overpredict the past temperature as warmer than it really was. So that was a lot to look at. We made a table to easily compare the performance of our 3 models. The simple linear regression currently used by scientists performed the worst in all 3 categories of correlation, variance, and MSE, which was assuring to see. Our fully connected and recurrent neural networks had different strengths. Whereas the fully connected model really picked up on the average historical trend, the recurrent neural network strength was capturing the relationship between temperature and time. It is thus of great interest to create a model that incorporates both of these aspects into one.
So looking forward, there are a few things we could do to improve the results we present here. First of all, we could just do some more hyperparameter tuning. So especially for the fully connected model, we tried to do some tuning of this, but the algorithm just wasn't able to finish within the time we had. So certainly an easy next step would be to finish that hyperparameter tuning and really get that model going with the optimal hyperparameters. In terms of actually altering the models, one common reason that these models can sort of underperform is because they don't have enough input data. And while we can't just manufacture more input data, there are a few strategies we can use here. First of all, we can reduce the number of things we're expecting our model to predict, which means we can kind of make the input data more dense and therefore be more successful at predicting the stuff we really do want to predict. So for instance, we are getting input data for a bunch of different coral species and for coral and trees across a wide range of geographical locations. And so that's really asking our model to do a lot. Not only does it have to predict the temperature, but it has to predict the temperature across the whole world given the latitude and the longitude, and it has to be able to understand all the different types of species we throw at it. So maybe there is a pre-existing model that can help to make sense of all these different species or this geographical variation separately, so we can condense all that input to a single column to our model and kind of make things more dense so that we're only predicting the temperature. Secondly, there are some things we can do to actually get more data. First of all, we could combine the coral and tree data and use both of those to train one model instead of treating these as two separate problems. Secondly, we could add the previous, for instance, D18O data and the next year's data to figure out whether there might be some sort of time dependence, whether the temperature for a given year might be better predicted as the result of input data across a window of years. Secondly, we could combine the features of the fully connected model, which again used this raw data from the coral and the trees, with the features of the recurrent model, namely taking into account predicted values from previous predictions. And if we combine those into one model, we might be able to get useful data from both and combine it and get a more useful result than we would have individually. Finally, there are other raw input data sources. So for instance, ice cores, where we basically drill down really deep in ice and analyze all sorts of things about the composition of the ice, or boreholes, which is just when you drill down really deep anywhere and just analyze the temperature really deep, are both established ways of doing climate reconstruction. So it's possible that by incorporating any of these signals into our model, we might get a more accurate result.
From the entire P-Climate team, we thank you for your attention. Let us know if you have any questions. Thanks.
Yeah, so thank you again to the P-Climate team for preparing that. Like they mentioned, if you do have any questions, please ask those asynchronously over email or messenger.
We actually have 3 other members present.
Oh, they're here?
Yeah, we have Nate, Rachel, and Gabe. Welcome, y'all. So if anyone has any questions, please feel free. Sorry to interrupt, Andy.
Yeah, all good. Cool. Yeah, if there's no question. Oh, sorry. Go
Hi,
ahead.
can I ask a general question, like about PAI in general?
We can save those for the end.
Yeah.
Oh, yeah, sorry.
Thank you.
Cool. In that case, let's pass it off to Kevin and Peter Resume.
Alrighty, thank you guys. My name is Kevin. I'm the project manager for P-Resume. My teammates were Evan and Aiden, who unfortunately could not be here today. But Evan, say hi.
Hey.
All right. So we'll start off with kind of like the motivation for this project. This project is based around leveling the playing field for employees, because employers have all sorts of automated tools that they can use to weed out our resumes when we apply. So we thought we'd create a tool for employees to kind of fight back. What were some of the main goals of this project was implementing sort of keyword search, because we know that keyword search is important for both employees and employers. We thought that was the way we could approach this, is look for those keywords. And the way that we're doing that is through a named entity recognition model, which means that it can recognize certain keywords from the resume based on keywords that we give it. We also thought about how we can make this tool more easily accessible. Accessible meaning not only easy to get, but easy to use, so that an average user wouldn't be putting more effort into this than they would in making hundreds of different resumes for each job.
Right, so just to recap, last semester, we created our first named entity recognition model. We tagged a mountain of job description training data, which we then fed into our named entity recognition model. And then we wrapped our model in a basic command line front end that we use to sort of create our finished product for the first semester. So just to recap a little bit on what it was like to gather the training data, basically our goal was to pull job descriptions from Glassdoor so that we could then feed those into the model. So we ended up creating a web scraper using Selenium, and basically pulled these job descriptions from the jobs on Glassdoor that looks something like the one you see at the bottom of the slide.
Yeah, so we started off with the scraper, and it was really important to us because we didn't have our own data. We had to kind of create a big data set to use. And last semester we had a scraper that worked, but it had a couple of key issues. Number one, depth. It wasn't able to get very far per search. We ended up having to make a multi-threaded application to that, but that wasn't ideal. It also wasn't very fast. It took all night to run, and it only scraped a couple hundred job listings. And that was because of the way that things were set up, which I'll talk about a little bit. And then lastly, we wanted to fix the reliability of it so that it wouldn't just crash on us because it encountered something unexpected.
So more specifically on the depth question, like Kevin mentioned, basically our scraper was sort of getting bogged down and would get stuck after about 100 listings. So what we did is sort of modified it in such a way that we would log into Glassdoor before doing further scraping. And so this would sort of get rid of a lot of these pop-ups that were getting in the way of scraping all the data that we needed, because a lot of these pop-ups were about signing in. And so this sort of not only got rid of those pop-ups, but also just emulated general human behavior more closely. And it sort of made the experience navigating through Glassdoor a lot smoother.
Here's a cool GIF of what that looks like. So you can see we actually were able to store our username and password as environment variables, and then it could just log in by itself. That also meant that Glassdoor thought we were humans instead of just bots, and it was a little bit easier to fool them. As for speed, so before we were using like a manual wait to make sure that the page is loaded, because Glassdoor is a web app, not all the elements had loaded at the same time. And so either we didn't wait and we had a crash, or we would wait a little bit and reduce our speed. The solution was to implement WebDriver wait. This meant that we're not waiting a set amount of time, but instead we're being flexible and actually asking the web page to make sure that it has already loaded all the elements that it wants to load. You can sort of see a breakdown of what that code looks like here. Importantly, XPaths are sort of the class names of the things that we're looking for. And so we can search by those. We can search by like job description and find that in the web page. And then we can tell it a max wait time so that worst case, we can just skip it. And that way we're not wasting extra time.
And finally, with reliability, we basically needed to make sure that errors didn't occur during scraping and ending it early. And this actually was a bit of a headache with Glassdoor because they tended to change some of the HTML stuff that was going on, and they would add new pop-ups and things. So what we did is we improved the logging. We added some retries and some sort of error handling code. And this just made it a lot more reliable and a lot smoother of an experience overall.
So overall, we were able to scrape a lot more data than last time. And this is kind of what it's going to look like now. We actually implemented a new category for new keywords called experiences. Skills and attributes were already here with us last semester. And so this is kind of the niche that they fill, is that the red experiences are tagged for things that you might find in your experiences section of your resume, whereas skills go in the skills section and an attribute might go in your manifesto or passion statement at the beginning. We also had to find a new way to tag this data because we had to tag it all ourselves and train the supervised learning model. We needed to find a good system to do so. Our old system only worked on Windows, which already made it super difficult, but it was a super slow and buggy system. We discovered this instead, which was a cool NER annotator specifically made for Spacey. We did have some hiccups though. When we ran this thing, because of all the dependencies that it had, none of our computers ran it the same way, and so we had different issues. The way that we fixed it was using sort of the magic solution called Docker. Docker is a container system, and so we were able to spin up a virtual machine sort of thing that we could share with everybody on our team so that everyone was working on the same sort of machine and had the same experience with it. And we could run it all using Docker Compose up, thanks to creating a couple of different containers to set everything up.
Right, so now that we had finished our new tagging and we were able to train our new model, and sort of we noticed a lot of performance increase with that, we were able to have some fun with it, and we sort of made a lot of progress on the front end. So we converted from a command line interface to a web front end, which was really exciting. So to do this, we just used Flask, which allows you to run Python code in web apps. And then we used some reusable HTML templates that we created ourselves to just sort of generate this content dynamically, and then cleaned it all up with a little bootstrap to make it look nice. And so we had the home page in the front, and then we have our results behind it of the tag data. But we'll dig into that in a second with our demo here.
So without further ado.
All right, so now we are running our new version of our app. So this is just a Python executable that is being run in the command line. And Flask is giving us a URL, so we're just copying that. And when we paste it into our browser, it will sort of open up the local server that's being run by Flask. So this is the home page. And as you can see, it sort of dynamically resizes. And we have job search query and job title. So in this case, we're searching a single job by the title and the company. And when we search it, it opens up Glassdoor using our scraper. And so we can sort of see the scraper in action here. It's sort of closing out of the pop-up, clicking on that first job. And there's going to be one more pop-up that it closes out of. And then now it is pulling the job description data. And as soon as that happens, right away, it feeds it into the model and shows us our output. So if we want to jump back to that output real quick.
Yes.
As we can see, there's a lot of experience and some skills and attributes. And obviously models are hard to get perfect. So, we have love in the skills, which is, work in progress, but we also have Python and AWS, which, is accurate. And then attributes, we have, self-starter and, things like that. And then experience-wise, we have REST, web service APIs, Android TV. So, we're pulling out some actual relevant information here.
Yeah, so we made a lot of progress this semester. I think there are definite ways to improve. The scraper could still use for more improvement, just to be able to scrape more and scrape further every time. And more and better responsive error handling could fix our work there. As for the model itself, we'd like to be able to better differentiate skills and experiences. Because we are tagging that ourselves, the way that the model differentiates it is based off how we do it. So having a better system for making sure that we're all tagging the same way would go a long way there. We also want to just tag more data. This year with only 3 members, we went a little bit slower on the tagging, but with more members, hopefully next semester, we'll be able to go a lot faster. And lastly, hyperparameter tuning is going to go a long way here. Because we had better data this time around, we were able to do things like drop the dropout rate so that it wouldn't ignore as many variables. But we'd love to take a look at seeing if we could change a lot more things, adding more hidden layers, perhaps changing the way we do optimization would all go a long way in making sure that our model is as accurate as possible.
As for the front end, we're thinking that it might be good to display more details for once we scan a listing, like or a specific job. Maybe we want more information on the company or the just various aspects of the job. We also think it would be really cool to output relevant information to maybe like a Microsoft Word document or a resume template or something to get the user started, depending on where they're at. And then finally, we think it'd be really cool to deploy this finished product to the web and actually get it out there so people can start tinkering with it and making use of it.
So for deployment itself, we'd like to move that to a Docker container system so that people wouldn't have to mess with all sorts of dependencies like we had to. And while we're doing that, we might as well integrate a file upload system so that we could have a whole packaged ready app that people could download and use immediately. Any questions?
So how do you make people aware about this now? Because this is elite.
Well, that's a good question. It's probably something that we'll be looking into more next semester. But it's super relevant already. So I think people will be looking for things like this pretty soon. And the faster we can have it hosted and the faster we can have it ready to go will be better. I mean, if you guys have seen like any news about like the recent like anti-work stuff on Reddit or the great resignation that they're calling it. A lot of this stuff is super relevant and people are already starting to create scrapers and automatic bots to fight back against companies. So I'm sure people will be on the lookout soon. I think I see a raised hand.
Yeah, so you're using a scraper to connect your program to another site that's like probably commercial, and like how do you deal with copyright issues?
Because this is a product that is supposed to just kind of like level the playing field, we don't want to commercialize this product. I accidentally moved the slide also, so sorry about that. But we'd like to release it under some sort of free use license. That's something we'll have to look into next semester once it's a lot more ready to go. But yeah, definitely, I don't think we're looking to commercialize this. Cool. I think I'll hand it back to you, Rune.
Awesome. Andy, can you share?
Yeah, one sec.
No problem. Congrats to all the project teams, by the way. This was awesome to watch. You guys did a great job. Yeah, so I can talk about our plans for next semester. So we're obviously going to continue the project train and have more projects and events, as you guys heard from some of the PMs today. There's a lot of potential to continue these projects, and there's a lot of cool and exciting ways in which they can be extended and improved. So we're definitely going to continue with that. And as we'll talk about shortly, we'd love to recruit more project managers. If anyone has any ideas to run an AI project, you're more than welcome to submit it in our website. We love AI, obviously, so we love the diverse ways in which AI can be applied. So any ideas you have are welcome. And now I can talk a little bit about the internships we'll be hosting with our industry partners. So yeah, our application for those is live. You can change it. And our first partner is TradeWeb, which is a financial services company based out of New York City. And the project which they'll be running is anomaly detection in their specified fields in their reference data, which will be financial data, obviously, which they haven't actually shared with us yet, so we don't exactly know what the data is. But the project will involve using ML techniques to sort of get those anomalies. Anomaly detection is a really big field in ML, as some of you know. So that'll be a super fun project, which will require lots of fun ML techniques and skills. And the liaison for that project will be the CTO of their company, who's a graduate of MUD, as well as their global head of data strategy, Lisa. And then our second partner is Samba TV, which is a TV analytics company. And they will be asking us to implement advanced methods in dataset labeling, where we will be looking at their TV data and their sort of image and video data and trying to supercharge the way of how we label it. And since most of their data is sort of video and images, there'll be a lot of cool techniques which will be applied for it, like computer vision, speech recognition, audio analysis, NLP. So this should be a super fun project, and the liaison will be their head of AI, whose name is Brian Cruz. And then our third and final industry partner is NavFees, which is an early stage startup, which was founded by Sam Malagon, who graduated from CMC in 2015. And that company is focused on modeling marine migration patterns like dolphins and turtles to essentially allow parties who occupy the ocean space, like fishermen, government research groups, to sort of understand where these species are migrating to. So that project will have two components, an ML component, obviously, where you're sort of using ML techniques like maybe GNNs, graph neural networks, to sort of model the migration patterns of these species. And then Sam has also let us know that he wants students to be exposed to sort of the bigger ML operations, which goes into deploying these projects. So you'll be exposed to techniques like Docker and those sorts of things. And you saw Kevin and Evan talk about Docker earlier, and Kevin basically alluded to the fact that it was I think you called it a magic solution, Kevin, is that right?
Yeah, it seemed that way to us.
Yeah, so students in this project will be exposed to Docker specifically, and I've taken a look at Docker too, it's super cool. So this project should be super fun. And if you're interested in learning more and applying, you can go to our website, our hiring hub, and you can see more detailed project descriptions for these three projects. I'm sorry, I kind of have to sped through it because we're running a little short on time here. And sorry, to answer your question, Abrar, yes, you can absolutely apply to these if you only know Python. In fact, that's sort of the big prerequisite for these projects. As is the spirit of AI on this slide, you can see like you don't need extensive ML experience to participate. So you can definitely apply if you just have intro CS experience. And yeah, on that note, our application process for these industry projects is actually open right now, and we want to recruit for those projects during winter break because we want to have those projects kick off as soon as the semester starts, so we have the max amount of time we can to implement them. So the project application is on our website right now. And just to remind everybody about the application process, you just need to have a passion for your project topic. You need to have the time to be able to commit to it, and then just intro CS experience is great. You can change the slide, Andy. Yeah, and before we get into any general questions, we have a guest with us. We know that you guys have a lot of cool ideas and are super passionate students who have great ideas, like you just saw the many cool projects which we just showed you. So there's a fund called Contrary, which is essentially looking to fund these ideas, and the 5Cs and CMC specifically have a partner for Contrary who's a student representative, and she's actually in the audience right now. Her name is Mihak, and she wanted to kind of explain it. So Mihak, you can unmute yourself, and if you have anything to share, please feel free to share your screen.
Hi everyone, just wanted to give like a quick 2-minute intro on Contrary. As Varun mentioned, you guys seem like a really cool group of students who are interested in AI, and I thought this might be a cool audience to share this kind of thing with. But essentially, Contrary is a university-focused venture fund which just invests in cool ideas that students come up with. And so our founding principle really was just that talent exists at the undergraduate level, and that talent isn't really being utilized because a lot of students don't have resources to take their ideas to the next level. And so that's where kind of we come in. And so there's a lot of different things we do, but the main things are funding student ideas, giving them access to work at really cool startups. We're actually backed by the founders of Tesla, Reddit, Airbnb, and lots of other cool startups. And so our network's really, really expansive, especially when looking for internship opportunities, and also connecting students with anyone they might want to talk to. So we actually have a fellows program, which gives fellows exclusive access to Contrary only events, networking, and things like that. But basically, if any of you guys are interested in learning more or know anyone who might be interested in this sort of thing, just feel free to reach out to me. I think Varun also put Contrary's website in the chat, so feel free to check that out. And then I'll also put my email in the chat. But yeah.
Perfect. Thanks, Mihak. Yeah, now we can take any questions anyone has about Pi or any of the industry projects or anything else. I believe somebody had a question earlier.
Yeah, I was the person who had a general question earlier, and yeah, you mentioned like intro CS experience, but like what exactly, could you explain like what exactly you mean by intro CS?
Yeah, so for example, CS5 at MUD suffices, CS51 at Pomona suffices. Just basically like, the basics of Python, like loops, recursion, basic data structures like lists, all of those things. Hope that helps.
Yeah, so if I don't have like that amount of knowledge at this point, then like, is there anything I can do related to PAI?
Yeah, you can come to our events. As we talked about earlier, if you were here, we host a variety of events related to AI, such as like we invite alumni to talk about their experiences. We talk about getting an internship in AI or data science, excuse me. But to participate in a project, if you don't have CS experience, it might be a little bit tough. So we'd recommend you to get that to be able to participate in a project.
And like, when do you usually like recruit people for projects?
Yeah, that is during the first few weeks of the semester. And yes, sorry, Marcos, thank you very much. We host ML workshops at the beginning of each semester. And Marcos leads those, and he does a pretty damn good job at it. So if you would like to come to the workshops, we'll be hosting them at the beginning of the semester, and you can also access them on our GitHub if you just want to take a look at them. And our GitHub is in our website. Did that answer your question?
Yeah, and like, can I ask one more question?
Yeah, of course.
So, you said like you're like recruiting people like in the middle of winter break, and like then you mentioned like you're like,
I'm sorry, I should have been
at the start of the semester.
I should have been more clear about that. So for our industry projects, which I just talked about, we want to recruit them a little bit sooner because we're working with an industry, they sort of have more deadlines. So we want to start the projects as quick as possible, because typically what happens is we take the first few weeks of the semester for our student-led projects, and then we sort of start the projects a little bit into the semester. So for example, this semester we started, I think it was late September, which was about a month after the semester started, because we wanted to take some time to sort of, we had to present at Turf Dinner, and Turf Dinner was super late this semester. So that's why for the student-led projects, which you just saw, they started a little bit late, and we recruit for them in the first few weeks of the semester. But for our industry projects, which I just mentioned, we want to sort of maximize the time we have for them. So that's why we're recruiting for them during the winter break. And we anticipate that we'll have a lot of interest for them. So that's why we're opening up the application really early. Does that help?
Yeah, and like this might be like a very unrealistic question, but like I'm planning to learn Python during winter break. Like if I do that, then like do you think it's like do you think I will be able to like participate in some kind of a student project after the semester starts? Or is it too short?
It depends on how much you learn. If you're just learning like the very, very basics, then maybe not. But if you go a little bit more in depth, then I guess it just depends on how much Python you learn. But honestly, I would encourage you to apply for the projects if you, regardless, you don't have to like, there's no penalty. Sorry, you can apply, anyone can apply for them. And if you have the experience, then you should be fine.
Yeah, and like I guess like you guys were active like last semester, but like I never heard anything about you like until like the middle of semester. So like where do you usually like spread news or like distribute this kind of information?
We have a mailing list. Would you like to be added to it?
Yes.
Okay, why don't you email me your email, or excuse me, put your email in the chat you can just send it to me personally and I can add you.
Okay, I'll send you my email.
Okay, thank you. Yeah, Huang asked a good question in the chat. What's the recruiting process for the industry project? It's kind of the same where you can take a look at the application on our website. It's pretty similar. You select a project you're interested in out of the 3, and then the PM who we've chosen interviews you. And if you're selected, then you join the project. It's just an added step of you're going to meet the industry liaisons who I mentioned earlier to get onboarded, and you'll have to sign NDAs because we are working with sensitive company data. So that's the only difference. Does that answer your question, Huang?
Yes, thank you so much.
Perfect. Any other questions? Let me check the chat. All right. In that case, thanks everyone for staying on and coming, and congrats to all the project teams on their work. You guys all did a really great job, and we're super proud of you all. Good night, everyone. Good stuff, Andy. Thanks for sharing.